All right, so this is section 1.6. We're going to be doing 3 sections this week, 1.6, 2.1, and 2.2. You'll see only homework on 1.6 for the online homework, homework from 1.6 and 2.2, because the 2.2 homework covers the 2.1 material. All right, but we will have 3 short-ish video lectures for this week. So 1.6 is about the fundamental identity. And it's an identity that involves sine and cosine that you've maybe seen before, but it's called a fundamental identity for justifiable reason. It's very, very, very important to for us in calculating and manipulating trig functions. All right, so let's take a look at where this guy comes from. So last time we talked about the definition of sine and cosine is if you take a circle of radius 1, right, and you take a point on the circle, let's say right there, and that point, this angle here, if this angle here is of size theta in radians, it has to be in radians, then the coordinates of that point is going to be cosine theta, sine theta. And that's the definition of cosine and sine. All right. In other words, this position right here, the x-coordinate is cosine theta. And that position right there is sine theta. Okay. All right, so that's the basic setup of the definition of sine and cosine. But one thing you can notice here is we actually have a right triangle going from here to here, there to there, right? That's a right triangle right there, and then from here to here. Okay, let's see. This because this position right here is cosine theta, we know that this length right there is cos theta. All right, because this height of this point right there is at sine theta, we know this height of this right triangle is sine theta. All right, we know this circle is radius 1, and so I know this hypotenuse is 1. Okay, well, the Pythagorean, let me draw the whole thing down here just because that might be a little messy. So my picture is, here's theta. This length is cos theta. That length is sine theta. This length is 1, right? The Pythagorean theorem tells me if I have a right triangle, then this guy squared, cosine squared, plus that one squared, sine squared, is equal to the hypotenuse squared, 1 squared. Okay. And so we conclude that cosine squared theta plus sine squared theta is always equal to 1. That's our fundamental identity. All right. By the way, this notation here, these two notations look a little weird. They just mean the square of sine and the square of cosine and the square of sine. All right. So this cos and then as 2 and then a power 2 theta. This is the same as cosine theta whole thing squared. All right. And this sine squared, this is sine theta whole thing squared. It's just alternate notation. And I think probably the justification for this notation is that oftentimes people are lazy and don't put the parentheses. And if you do that, cosine theta squared looks like you could have some confusion, right? Does this guy here mean cosine theta whole thing squared? Or does it mean cosine theta squared like that? Like you're squaring theta and then plugging it into the cosine. So because of this ambiguity, or this possible ambiguity, if people are lazy about parentheses, which people are, there's this convention that when you square a sine function or you square a cosine function, you put the square in front of the cos or in after the cos or after the sine. All right, purely notational, and it's purely to kind of avoid silly errors. Okay, in any case, the conclusion here is cosine theta plus sine theta is always equal to 1, no matter what the theta is. All right, so let's check. Let's check if this is the case for some cosines and sines that we already know, right? Let's see. We know cosine of pi over 3, right? We know sine of pi over 3. right? Cosine pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. This is from that table that we talked about that hopefully you'll have kind of memorized by now. Let's see. If we square these two, so cosine squared pi over 3 plus sine squared pi over 3 squared pi over 3, right? If this kind of fundamental identity were to be true, this guy down here better be equal to 1, right? So let's just check if it's actually the case. So this is equal to cosine squared pi over 3 is cosine pi over 3 whole thing squared. So that's 1/2 squared plus sine squared pi over 3 just means sine pi over 3 whole thing squared, right? And so what is that equal to? That's 1/4 plus cube root of 3, square root of 3 squared is 3. And then square root of 2 is 4. And so this is equal to 1/4 plus 1/4 plus 3/4. So that's 4/4, which is 1. Okay. And of course, if you check it, this for other thetas that we already know how to compute the sines and cosines of, you'll see that this certainly works for all of them. All right. Let's use this in an application. So we'll just do one application for this section. If you do read this section in the book, you'll notice they also talk about a way to compute sines and cosines of kind of strange looking angles, like angles bigger than 90 degrees, bigger than 180 degrees, bigger than 270 degrees, using what they call reference angles. I hate it. I'm not going to talk about it at all because it involves basically just memorization and without understanding. And it involves kind of it's very heavily dependent on kind of the unit circle idea of cosines and sines. I know a lot of people kind of have memorized this unit circle thing where you kind of memorize all these angles, pi over 6, let's say, pi over 3, pi over 2, and so on. And then you've memorized perhaps the sines and cosines of these angles. I think that's a terrible way of looking at sines and cosines. We're going to, in section 2.1, work with the graph of sines and cosines. And from here on out, that's really how you should be always thinking of sines and cosines in terms of their graphs. All right. So this unit circle idea, not the definition, I don't mean the definition of sine and cosine. I mean kind of this idea of memorizing angles and how they relate to each other in terms of sine and cosine. I think that's absolutely terrible. So I'm not going to do it. All the information that you will have gotten from 1.6, the reference angle section, you can get from the graph. All right, so we won't have lost any kind of knowledge. All right, so our application here is very simple. Basically, the idea is that let me rewrite our identity, cosine squared theta plus sine squared theta is always equal to 1, no matter what theta is. What that tells me is if I know, for example, one of these, I know sine of theta, then this tells me I can figure out cosine of theta. All right. Or if I know cosine of theta, then I can figure out sine of theta. Right? Because if I know one of them, then I can solve using algebra for the other one. All right. So an example would be a problem like this that you'll see on your homework. What is cosine of theta given that we know sine of theta is equal to, let's say, 5 over 13. Okay. Sorry, I need one more bit of information. And theta is in quadrant 2. All right. So in this particular problem, this is kind of an interesting problem because we don't even know what theta is. We only know it's in quadrant 2, right? And we know sine of theta is 5 over 13. Okay. So the question is, what is cosine theta? So we use the fundamental identity. So we know cos squared of our angle, theta, plus sine squared of our angle, theta, should be 1. We know sine of theta is 5 over 13, and so we can plug that in. We get cosine squared theta plus 5 over 13, whole thing squared, should be 1. And so cosine squared theta should be 1 minus 5, over, that should be a 13, over 13 squared, right? And let's just calculate that right-hand side. That's 1 minus 13 squared is 169. I guess I could, let me just leave it as 13 squared. And then 5 squared is 25. All right. If I do common denominators, I'm going to get 13 squared on the bottom, 13 squared minus 25 on top. All right. And these are kind of ugly looking numbers, but they're just numbers, right? So it's not too terrible. This is 169 minus 25. And this turns out to be 144 over 13 squared. But 144 is 12 squared. So this is 12 squared over 13 squared. All right. And the reason I wanted to write it like that is because that's 12 over 13 whole thing squared. All right. And so what I get is cosine squared is equal to 12 over 13 whole thing squared. And so cosine theta is equal to square root of the right-hand side. So square root of 12 over 13 whole thing squared, right? Plus or minus, okay? Remember, anytime you square root both sides of an equation, you need to pop out a plus or minus, all right? So this is going to be square root of 12 over 13 squared is 12 over 13, so plus or minus 12 over 13, all right? Okay, maybe I did this a little too fancy. I guess maybe a more pedestrian way to do it would be like this. This would be 169 and then 144. And then what you would end up with is cosine squared theta equals 144 over 169. And then I would get theta equals square root plus or minus square root 144 over 169. And then you figure out what those square roots are, right? It's just that I kind of knew that it would turn out to be a nice square. So I took advantage of that fact. But generally, perhaps you don't know. And then you would have your answer like this. And then you would start to simplify and then maybe realize that it's actually a nice 12 over 13 squared. In any case, what we get is cosine theta is equal to 12 over plus or minus 12 over 13. Should it be plus? Should it be minus? That's what the last bit of information is there to tell us. Theta is in the quadrant 2. All right. So what does theta being in quadrant 2 mean? That means that theta lives somewhere here, right? Theta is an angle in quadrant 2, so it's perhaps something that looks like that. All right. Okay, it's between this vertical and that horizontal. All right. So why do I care about that? Well, theta being here means that the point on the unit circle that helps us define what sine and cosine are, right? So let's say this is a radius 1 circle. That point there, again, it has coordinates cos theta, sine theta, right? By definition of cosine and sine. Well, what's cosine theta in this case? Cosine theta is right there, right? What is this? This is a negative number because it's on the left of the y-axis, right? There's 0. These numbers here are all negative. Okay, so knowing that this angle is in quadrant 2 tells me that cosine theta should be negative. And so that means I need to keep the negative sign and toss the positive. All right, so theta in quadrant 2 tells me cosine theta is less than 0, right? So that means I keep the negative, right? And let me write toss the positive. So cosine theta is equal to 12 over 13. Okay. So we can figure out cosine theta without even having to ever calculate what theta was. All right. Let me do one more example, and that's the core kind of content of this section. So let's say what is sine of, and let's use a different angle name this time, alpha. if cosine alpha is equal to minus 1/5 and alpha is in quadrant 3. All right, so same type of problem, but this time we're looking for sine and we're given cosine. So again, we have sine squared of alpha plus cosine. I guess I wrote it as cosine squared sine squared. Okay. It doesn't matter, of course, what order I write it in, but let me just keep it consistent for this lecture. So cosine squared alpha plus sine squared alpha is equal to 1. Let's see. We know that cosine alpha is minus 1/5. So this guy here is, let me not be lazy and just write it out. So this is minus 1/5 squared plus sine squared alpha is equal to 1. So this is going to be sine squared alpha is equal to 1 minus 1/5 whole thing squared. This right-hand side is 1 minus 1/5 squared, just because the minus sign when you square it goes away, which is 1 minus 1 over 25. And doing common denominators, this is going to be 24 over 25. All right. So sine squared alpha is 24 over 25. So sine of alpha is equal to, I square root both sides. And again, when I square root both sides, I got to pop out a plus or minus because there's always two answers to a problem, right? So this sine squared alpha equals 24 over 25 is saying I have a number, sine of alpha, and when I square it, it's 24 over 25, right? So there's always two possibilities because there's always whatever answer you get that's positive, the negative version will when you square it, the negative number will go away, so you get the same answer. So there's always going to be two answers when you do this. All right, so you got to remember the plus or minus. 24 over 25. All right. Okay, now again, we need to figure out, should it be plus or should it be minus? We think about this information here. Alpha is in quadrant 3, so that means alpha is down here, right? Alpha is something like that. It's between this arrow and that arrow, right? It's let me shade it in. It's somewhere in here, right? And if you think about our definition of sine and cosine, right? We look at a unit circle. That point right there has coordinates cosine theta, sine theta, by definition of cosine theta, sine theta. Cosine theta is right there, right? So that's the coordinates of cosine theta. That's the coordinate of sine theta, right? By the way, we were told alpha. Alpha. We were told cosine alpha was minus 1/5, right? So actually, I know this point right there is minus 1/5. Okay. All right. In any case, sine of alpha is right there. It's below the x-axis, right? These are the negative y values. And so I know that sine of alpha has to be negative, right? Because let me write like the sine of alpha in the third quadrant, right? Because every point on the circle in the third quadrant, every point in the third quadrant, in fact, has negative y coordinate. Okay, so sine of alpha should be negative, and so that means we toss the plus sign and we keep the negative sign. All right, and so sine of alpha is equal to negative square root 24 over 25. All right. Okay, so that's a very nice application of our fundamental identity. We're going to be using the fundamental identity all over the place in the future, but here's a nice kind of smallish introductory example of how it could be used to do some calculations that perhaps otherwise might not be as kind of simple. Actually, let me mention another kind of point of view of this, the same thing. So let's look at the same problem. So here I have this is my angle alpha. I said that this point right there was minus 1/5, right? That tells me, so this was my, that tells me this length here is 1/5, right? The length of that segment, right? And if I use this as 1, right, radius, circle of radius 1, just the same picture up here, then I can actually use the Pythagorean theorem to figure out that length right there, right? So the Pythagorean theorem would tell me, let me call this question mark, 1/5 squared plus question mark squared is equal to 1, right? And so question mark squared is equal to 1 minus 1/5 squared, which is 24 over 25. And so question mark equals plus or minus square root 24 over 25, right? And then again, we know that this is in the third quadrant, so the answer should be a negative number, blah, 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 right? So this is a kind of a geometric version, right, using triangles to do the exact same thing. But it's good to get used to working with sines and cosines and always kind of remembering that cosine squared plus sine squared is equal to 1. So obviously, either way you do it, you're pretty much doing the same thing. But I think for this section, think of all the problems in this particular way using the fundamental identity so that you get more kind of comfortable with it.